Hello everyone. Today I will walk you through the Measnet assessment standards, which provide a structured and standardized approach for evaluating wind resource and energy yield assessments. In wind energy projects, the uncertainty directly impacts the final financial decisions. Therefore, following a standardized methodology like a Measnet ensures the transparency, consistency, and bankability of results. This presentation will focus on the full life cycle of wind resource assessment from measurement to final energy estimations. One of the fundamental principles of Measnet is the concept of traceability chain. Every step in the wind resource assessment must be documented, reproducible, and auditable. This chain starts from the site selection and instrumentation, data measurement and validation, wind flow modeling, energy yield calculations. In any step in this chain is a weak or inconsistent, it introduces an uncertainty that cannot be justified later. For example, if the measurement data is not traceable to calibrate instruments, the final energy yield becomes questionable. So, the traceability chain ensures that each point or each output is backed up by a verified inputs. Before installing any measurement equipment, it is crucial to understand the site itself. The site characterization includes topography, surface roughness, and obstacles. So what does the topography means? In the topography, the elevation changes, slopes and ridges will take into an account. And in the surface roughness, we have the vegetations, forest and water bodies. And in the obstacles, like buildings, trees and terrain features. These factors influence directly on the wind speed distributions, turbulence intensity, flow separations, and speed up effects. For instance, a ridge can accelerate the wind speeds while a forest can reduce them and increase the turbulence. Proper site characterization ensures that measurement locations are representative, wind models can be applied correctly. Neglecting these steps can lead to a major error in the energy estimations. Representative radius. A met mass measures a wind at a single point, but a wind farm spans a large area. The representativeness radius defines how far the measurement can be reliably extrapolated, horizontally extrapolated. This depends on the terrain complexity, surface roughness variations, elevation changes. In a simple terrain, the mass may be representative for approximately 8 to 10 kilometers, but in the complex terrain, the representative radius is much smaller. Maybe it depends on the terrain or it is less than 2 to 3 kilometers basically. If the turbines are placed beyond this radius, measurement error increases and the model uncertainty increases. Therefore, the multiple mast or remote sensing devices like LiDAR may be reduced or required for a large or a complex terrains. Compliant metmast design. The design and installation of the meteorological mast must follow a strict standards. Key aspects include proper boom length and orientation, avoidance of tower shadow effects, correct sensor placement. For example, anemometer must be mounted facing the prevailing wind directions. Sensors can be placed at different heights to capture the vertical wind profile. Even a small design flaws can introduce a systematic measurement errors which cannot be corrected later. Hence, Measnet emphasizes standardized mast configurations, proper documentations or installations. All sensors used in the measurement must be calibrated and traceable. This includes cup anemometers, for measuring the wind speeds, wind vanes for measuring the wind directions, the temperature and pressure sensors. Calibration ensures that measurements are accurate, data is comparable across the different projects. Additionally, sampling the frequencies should be at least 1 Hz. Data should be stored as a 10-minute averages. Uncalibrated or a poorly calibrated sensors can introduce a bias which directly affects wind speed estimations and energy yield predictions. Data integrity risks. The data integrity is a critical aspect of wind resource assessment. Common risks include sensor failure, data gaps, incorrect data processing. If the data processing is not standardized, the results become a non-productive and uncertainty cannot be quantified. For example, improper filtering can either remove a validating data, retain erroneous data, and it will extrapolate this erroneous to the energy productions. Measnet requires that all data handling steps are documented, any assumptions are clearly stated. This ensures the transparency and reliability of the data integrity. Data integrity has a different classes as you see in the presentations, class E to class E, which is bifurcated or classified based on the um, uh, representativeness of the Measnet in the data measurements. Data refinement. Raw measurement data is never perfect. It must go through a data refinement processes which include a quality control checks, removal of outliers, filtering based on wind directions or a sensor shadow, gap filling using statistical methods. The goal is to create a dataset that is accurate, representative, and free from systematic bias. Special care must be taken to avoid the seasonal bias and overfitting during the gap filling. This refinement dataset forms the foundation for all the analysis. Wind measurements are typically extrapolated, to the long term using the long term measure, correlate, predict methods. Wind measurements are typically available for only 1 to 2 years or a very short period of time, but energy predictions require a long-term data. This is addressed using measure, correlate, predict methods, where we will take the measurement data and the reference long-term data. The reference long-term data may be an RFI data, MERA data, or any reanalysis data sets basically. The steps include here is the correlating on-site data with the long-term reference data, establishing the statistical relationship, predicting the long-term wind conditions. Reference dataset can include reanalysis datasets, nearby long-term measurement stations, and the accuracy of the MCP depends on the quality of correlations and length of overlapping data. A poor MCP model can significantly distort a long-term energy estimations. The extrapolation, there are various extrapolation methods which is used in order to see the statistical evaluations between the site measure data and the long-term data. Few of them are the linear regression, matrix method, and energy indexings, and neural network and distribution scalings basically. What are the key considerations in the while doing the extrapolation methodologies is directional dependencies of wind, seasonal variations, and stability of correlations. No single model works best for all the sites, therefore model selections must be based on the data characteristics and validation performance. The aim is to minimize the prediction error while maintaining the physical consistency. To estimate the wind conditions at the turbine locations, we use wind flow models. These models simulate how wind interacts with terrain, roughness, and obstacles. Types of models include linear models, example WASP, and CFD models for a complex terrains. The choice depends on the terrain complexity. Maybe like a simple terrain can be evaluated using the linear models, like a WASP model, and the complex terrain can be evaluated using the computational fluid dynamics, like in a wind sim. Accurate modeling ensures a proper turbine siting, reliable energy estimates. Extreme events estimations. In addition to average wind conditions, we must estimate extreme wind events. These are very crucial for turbine design and structural safety. Typically, we estimate a 50-year return period wind speeds. Statistical methods used include a Campbell distribution, peak over threshold method. Using a multiple methods help validate results and reduce uncertainties. Every step in the process introduces the uncertainty. These uncertainties include the measurement uncertainty, the modeling uncertainty, the MCP uncertainty, etc. The Measnet provides guidelines on how to combine these independent uncertainties in terms of a root mean square or a sum of squares and correlated uncertainties in linear summations. Quantifying uncertainty is essential for risk assessment and financial modeling. It directly affects the project bankability. The final outputs of the assessment includes like a long-term wind resource datasets, extreme wind conditions, energy yield estimations, and uncertainty breakdowns. These outputs are used by the developers, investors, and lenders to make the informed decisions. To conclude here, the wind resource assessment defines the energy input, while energy yield assessment translates into the financial output. Following the Measnet standards ensures the high quality data, reduced uncertainty, increased investor confidence. Ultimately, it bridges the gap between energy engineering analysis and financial decision making. And thank you.